So I'm just going to get the questions and work through them. The first thing I need to do is get into Logger Pro and open up a video. And I'm just going to, I'll steal that from 5.6. And insert movie down to Student Common, Stapleton. Physics 200, 856. I'll just take this one. Hopefully this is a fantastic video. It's, I forgot to see what it was called. I should do that. Oh, did anybody see what the name of this video was? That's not good, because I need to know what it is so I can find it in QuickTime. Delete. You would think I'd be right back in that same folder again, but I'm not. Okay, I'm going to pick 322. I need to remember that number.
322.
322. Oh, that was, of all the videos, why did I have to pick that one? That was a screw up. I'm sorry. It's good for you to deal with adversity. You know, maybe I should just use one of these. These are. This is from another class.
Do Jenna and Justine.
Connor, Jordan, Daniel. I'm going to do Grace and Katie's. I want to see this. I was just kind of wondering about theirs anyway. They were asking me something about it. So, and I know they've already done the work. Okay, so here's what you do. First, right-click on it, set the movie options, override frame rate, 480.
Whoa.
Yep, you're going right-click.
Yep, right-click on it,
Yep.
and then set the movie options to 480. The little sheet that I gave you says to do that. Then I'm going to use this. Oh, first, I'm going to click on these movie tools and select the horizontal ruler to set the scale, drag horizontally across, and that should be 8.8 meters. So I'll type 8.8. So now I've got the scale set up, and I've got the frame rate set up. So I'll move this slider. I'm dragging it forward until I see it move. And I don't get very precise control with the slider, but that is what it is. So I'll go back to right before it launches. Then I'm going to use these double arrows and keep clicking until I see the first little puff of smoke. Or it's actually a puff of water. There we go. So I'm backing up, somewhere right around there. Now this is just a nasty pixelated blur, but it's as good as it gets. So I'm going to click at the top of the rocket. So that marks the spot where water thrust begins. And now I'm going to go until all the water is out. I can tell when all the water is out because this column of water right here, it's going to get hit by the air escaping after all the water's gone. And that happens right there. So I went past it. I'll go past it a little more and then I'll go back. So that puff, that white we're seeing now is because all the air is coming out and hitting the water. And it starts right there. So I'm going to do another click, except I've kind of, in my mind, I've lost where the top of the rocket is. There it is. So these two dots represent the starting position and the end position of when the water thrust goes on. It's not for very long. Their thrust doesn't last long at all. They must have not had much water in it. Ones with more water, you're going to see the puff higher up. So I've got, now I can do number one. So number one on my sheet, actually I'll just write these down as I go. I'm moving the movie over, getting to my data, and my initial Y is 1.269 meters, and Y changes to 1.792. So I just subtract, and that gives me hey, I can't turn this on. Oh, there we go. That's the on button. That gives me the Y displacement. So 1.792 minus 1.2694. So it's, oh, I did it wrong. Well, maybe I don't even, I'm not going to do all the calculations, but that's how you do it. You just subtract this minus this, and that tells you how many meters this is. So that's number one on the sheet. Number two is what's the delta T? Delta T is this time minus that time. 9.769 minus 9.725. It's going to be a really short time interval. And I don't entirely trust it, but it'll be close enough. And then for number three, the average acceleration during the water thrust phase. Once you've got the displacement and the time, you can use this formula I was writing over here on the board. So that it's delta y equals v0 yt plus 1/2 at squared. But if you solve it for a, you get delta y times 2 over t squared. So you plug in, this should be delta t. Plug in your delta t, plug in your delta y, and multiply by 2, square that, and then you'll have the acceleration. So number 4 on the sheet, rocket's mass at the beginning of the water thrust phase. For that one, you just use whatever your rocket mass is. In grams, convert to kilograms, and then add a gram for every milliliter of water. So 100 milliliters of water would be 100 grams or 0.1 kilogram added onto the mass. Number 5, the rocket's mass at the end of the water thrust phase would just be whatever it is when it's dry. So right here, its mass here is the dry mass plus the water mass. Here it's just the dry mass. Number 6, you average those two masses to get the average mass. And then number 7, to get the net force acting on your rocket, you just use F equals ma.
What number is that?
Number 7. And to get the force, you just use the average mass of your rocket while the water's coming out, times the acceleration that you calculated earlier, and that'll give you the net force, at least the average net force. Then the weight's straightforward. The weight of your rocket is just the mass, the average mass, times g. And then number 9, to get the thrust, I realize this is a little more complicated than I was envisioning it, but we're going to keep it a little bit simpler. For the thrust, you've got thrust going up, and what's opposing thrust? Yeah, the air resistance. We don't really know what it is right now, plus it's pretty slow, so let's just throw that out because it's not good. We're not in a position to determine it. We could, but it'd be too much trouble. So let's just say we've got thrust and we've got weight. So we're approximating things here. And then the net force equals the thrust minus the weight. So if you've already calculated the net force and you've calculated the weight, we've got this and we've got this, you can solve for the thrust. So just do a little bit of algebra there. And then that takes you to number 9. Number 10, once you figure out what this thrust is, you just have to convert a 150-pound person to newtons. Figure out how much weight a 150-pound person would have in newtons, and then see how many times the thrust, how many times you'd have to multiply this thrust by to get that. So if your thrust is 6 newtons and this person is 36 newtons, then it's going to take 6 bottles to lift them. It ends up being not very many bottles. Divide. Yeah. All right, so that's the first page. The second page is all about the coasting phase. So for the second page, then you start to do more data points. Notice I'm using my little finger over there to click on the border of this so I can open this up because I don't want to accidentally click points. I'm just going to start advancing this, maybe 2 or 3 frames at a time because it's easier for me to precisely click. Don't click every frame because you'll be clicking right on top of where you clicked the last time. And I'll just keep doing this until I think my velocity is maxed out. And this is not a precise thing because you can see this rocket is really difficult to pick out against the sky. So I'm going to check my data points. Look at my velocities. Does it look like I've gotten up to a maximum velocity and it's stabilized?
Yeah.
I'd say so. So it looks like it's getting faster and faster and faster here. Somewhere right around here it's kind of maxing out. So on number 11, where you're asked for the maximum velocity, what I would do is just take a few of these numbers right in here and average them, or just pick something right in the middle. It looks like about 36.5-ish, just looking at mine. But if yours are all over the place, just select a few, take them, put them in a spreadsheet and average them. Then you convert that to miles per hour, you can do that. So now number 12 asks, what's your rocket's delta Y up to the moment that it reaches its maximum velocity? I'm going to say the maximum velocity is reached right here. Does that look like a reasonable cutoff? Yeah. Okay, so that's kind of what you do. This doesn't matter much because it's reaching it so fast. What we're doing here is not too important. But let's say right here is, I'm just saying it's reaching maximum velocity. I want delta Y. Y is now 3.145. Y started at 1.269, so I'd do 3.145 minus 1.269. That gives me the delta Y. It's something like 2 meters. So this rocket's traveling up 2 meters to get to its maximum velocity. And after that, it's coasting. So this next one says use QuickTime to do this. You know, you don't actually have to use QuickTime. Some people have used this program. If you can see the rocket okay in this, you can just skip some of the things in QuickTime. Keep advancing it until you see the rocket come down. I'm not seeing the rocket. So I'm going to have to use QuickTime. But you could click on the rocket right as it hits the ground and you can get a time from that. But, okay, Dakota, do you remember what it was?
No. It was like 3, 5, 6 or something.
Oh no, it was Grace and Katie.
Oh, yeah. It's fine. Everything's fine.
Okay, so now I'm in QuickTime. Everything hopefully will be fine. They're Grace and Katie. So I want to make sure I can see the rocket come down. I think I can, because I think they did this earlier and they could. Yeah, oh, I can see it. I don't know if you can see it on the projector, but I can see it on the screen. So I'm going to work backward here. I'm going to go to the point where it hits the ground. It's coming down. And right now I'm just trying to get what I'm going for is total time aloft. So it hit the ground right there. So you need to hit frame number on the bottom left here. Get this in frame number. This is frame 8,619. Now I'll go back to the beginning, and this is frame number 4,669. So I just subtract 8,619 or whatever it was, minus 4,669. And that would give me the number of frames. But how do I get the seconds? Divide by 480, because there are 480 frames per second. So that number 13, I don't know why I did this. I kind of ask you these in an opposite way. 14 would be the number of frames. Do that first. And then for 13, you divide by 480. And I don't know why I'm suddenly asking you what the rocket mass is after all the water's left, but I am. So now, you go to your spreadsheet, which I have sent you. This is maybe the most confusing part of all, because you've got to change these things. Remember I told you we're not even going to worry about the y dimension? So, or sorry, the x. So we're going to put in 0 for x velocity, for initial x velocity. And whatever it is that you came up with when you decided on the maximum velocity over here, I think I decided it was 36.5. That's what I'm going to put in here for y velocity, 36.5. And whatever the mass of my rocket was, this would be the empty mass. So for a lot of rockets, it was 0.13, something like that. Leave the air density, cross-sectional area, you know what that is. Starting time, that would be the time at which I reached this velocity. So I think we found that earlier. It'd be this minus that, which is about 0.1 second or something really small. What's that? I'm just getting you set up to do the whole rest of the page, number 16 through 20. So starting time, I'll just put in 0.1. Initial x position, we'll just make that 0. We're getting rid of everything in the x dimension. Y position is back, it's number 1 from the previous page, which I think I came up with is about 2 meters for this rocket. So all of these are the initial conditions after water thrust. And the rocket's just going to continue going up and then come down. So I don't know. Oh, this cross-sectional area is bogus. That should be something like 0.008 or less. So what I've got here is a time aloft of 6.36 seconds. I put in a coefficient of drag that's different until I get the actual time aloft that was recorded in my video. So if you look at number 13, I'm just going to keep adjusting. Let's say number 13 was 7 seconds. I'm going to adjust this drag coefficient so that this becomes 7. And if everything was done correctly, then I'll have found the right drag coefficient. Ooh, what did I do there? 0.08. So once my actual time aloft matches up with the real time aloft, then theoretically I've found the drag coefficient.
Until real time aloft
matches the one that it says here. So I keep on adjusting drag coefficient until this number matches the number that I wrote down in number 13. And to get terminal velocity, you can just read that off. It's right here. And the velocity when it hit the ground, you would just go back down to the spreadsheet and go to y velocity right here, and scroll down until the y position over here is 0. When the y position is 0, right now it's 44, it's getting higher, it's going to go back down soon. When that y position gets to 0, I'm going to go over and look and see what my y velocity is. So my y velocity is negative 31. And so this is the velocity when it hit the ground. If that's the terminal velocity, negative 57, then it did not reach the terminal velocity. And then there was one other thing. You were supposed to compare the maximum height here. You were supposed to write down the maximum height and then compare that to the simulation. And I'll just stop there.
Thank you.
So yeah, you're welcome. Sorry it's hard. Life is just so hard.